I'm the chairman of this session, and we begin the first fight of this morning. Each team, please introduce yourself. Reporter, please.
Hello everyone. Our team Google from Untitled Chapter High School. We wish to have a great debate and learn from each other.
You have to introduce the member of your team.
Okay, so I'm the captain of Team Google, and my name is Gong Ren. And this is 我们一群陈柏宇、曾宏and 郑宇轩。
Okay, thank you. And please introduce yourself.
Hello everyone, we are team 完美小猫 and I'm the captain 陈宇翔 and this is 陈玉、杨鼎阳、张新文、Josh Lee， 谢谢。
Okay. And the reviewer, please introduce yourself.
Hello everyone, we are Jin Zong Xiwan from Chuncheon High School, and I'm Zhang Yijun, and he is He Kai, and she is Zhang Yixuan, and he is Yu Xinzi, and he is Zhang Ruyu. And hope to have a good play.
Okay, thank you. Let me introduce the jury. I am Haikang Zhang from National Taiwan Ocean University. And please, Professor Guan. Professor Guan Xisheng from National Taiwan University. And Professor Chen Hong Li from National Taiwan Normal University. And Professor Yu Jingzhong from National Kaohsiung University. And Professor Zhuang Zhenhao from Danjiang University. And Professor Li Guohan from Chida Puso. Okay. Because a little late, so we begin the fight. So the opponent, you have 1 minute for challenge the reporter for the problem. Please begin the challenge.
We would like to challenge problem 5, single nice candle.
Problem 5. 评分表，你们放地方。
We'll accept the challenge.
Okay. So the problem is number 5. So each team please write down the representative name on the board. So reporter, you have 5 minutes for the preparation.
但是因为你刚刚打字，
脑抽。
然后那超问题，那你去做到那个，然后我去做那个，然后你做到一个。
关，不然他看不清楚。
什么都按。
对啊，它是这种方向。
没有，我看这边这个，因为我现在看不清。
对啊。
还好，这边。好到两边都开。这样子可以吗？不然这样公平。黑板的可以。黑板的可以。Okay, please take the floor. Please.
Honorable judges and distinguished competitors, I'm today's reporter Neil Jern from Team Google. And now I'm going to talk about the problem number 5, synchronized candles. So here is the problem statement. Oscillatory flames can be observed when several candles are next to each other. Two such oscillators can couple with each other, resulting in phase or anti-phase synchronization, depending on the distance between the set of candles. Explain and investigate this phenomenon. So my main focus will on how to make the candle flame oscillate, and the second is the investigation of the parameters. So here's my outline. First we have the observation and also experimental setup, experiments, theory and discussion, and conclusion. So here comes to the experimental observation. When the candle is burning, it will heat the nearby air and let the air rise. The hot air will drive the nearby airflow and make the cold air come to replenish. So you can see that the shape of the flame is pointed, which is formed by an updraft next to it. If there is no gravity, since no heat convection, the shape of the flame will be spherical and the combustion will be less intense. So we get that the thermal convection plays an important role in the burning of the candle. When there is only one candle burning, it will be stable and will not oscillate. When two candles approach and start to act on each other, they will start to vibrate up and down due to the thermal convection. So we see the two candles of these as an oscillator. So that's we observe the interaction between two oscillators. When two bundles of candles are closed, it will show the in-phase synchronization. Initially, the flame is at the shortest, and then it will gradually increase. Even we will see the flame spread out, and then back to the shortest. When the distance between the bundles of candles increases, it will show the anti-phase synchronization. At the beginning, the left candle is the shortest, and the right candle is the largest. And then the left candle increases, the right candle reduces. And when the left candle reaches its maximum, the right candle is the lowest, and vice versa. The flame change is opposite to the candle on the other side. Phase-free bifurcation between in-phase and anti-phase synchronization is depend on the distance between the candle bundles. So here's my experimental setup. We place bundles of candles on the 100mm translation stage to adjust the candle spacing, and the distance we change between the candles is 12.5 to 77.5mm. And the diameter of the candles we use is 12.5mm. We also use the tracker to check the motion of the wick. We set up a Schlieren photography to observe the hot air changes around the candles. And the light source of the Schlieren's device is a divergent laser, reflected by the 25cm contact mirror. Focus on the sleeve and focus on the screens. And below are the photographic patterns of 1 to 4 candles. As you can see in the picture below, when there is only one candle burning, the hot air changes around the candles will be steady. When there is more candles when there is more than 2 candles burning each other, the hot air changes around the candles will be rises intensely, and it will cause the flame oscillation. So that's we observe the interaction between the two oscillators. So here comes the experiment. We have in-phase, dead phase, and anti-phase synchronization. When the distance between the bundles of candles is the closest, which is 12.5mm, it will show the in-phase synchronization. As you can see in the videos, the flame burns cross-violently and even spread out. So we use the tracker to track the motion of the flick, and here is the trajectory tracking diagram of the flame. So the blue dot is the trajectory of the left candle flame, and the gray dot is the trajectory of the candle flame on the right. You can see that their trajectory all completely overlap, which means their phase difference is close to 0. When the distance increases to 20mm, the combustion will be less intense. As you can see in the figure below, the vibration amplitude of the flame becomes smaller, and the phase difference is still close to 0. When the distance, increase the distance between the bundles of candles, it should enter the antiphase area. But we found that before entering it, there will be an area where the airflow is stagnant. So in our experiments, the area is about 25 to 27.5mm. As you can see in the video, the flames is almost quenched. That's trajectory tracking diagram. The vibration amplitude of the flame is almost dead. When we keep increasing the distance to 30mm, we will enter antiphase synchronization area. So in the video, you can see that when the left candle is the highest, right candle is the lowest. And when the left candle is the lowest, the right candle is the largest. And the vibration mode of it is opposite. So in the trajectory tracking diagram, you can see that their period is 0.0779 seconds, which is slightly shorter than in-phase synchronization. When the distance increases to 32.5mm, the combustion will be more intense, and both are also anti-phase synchronization. When we keep increasing the distance between the bundle of candles, it will enter. The combustion between the flame will be more intense, as you can see in the video. Up to 57.5mm, the flame is still quite intense. Even we will see the flame spread out, and both are also anti-phase. Extend the distance to 62.5mm, the combustion becomes less, as you can see in the trajectory tracking diagram. In addition, if we keep increasing the distance between the bundle of candles, it will show the irregular beating, and the beating of two oscillators is not related. So here comes to the theory and discussion. We know that when the candle is burning, it will heat the nearby airflow, inducing updraft, and the airflow will come to replenish. So in our experiment, the in-phase area is about 12.5 to 22.5 millimeter. If another pair of candles exists in this area, it will show the in-phase synchronizations. From the Schlieren photography below, you can see that the hot air changes around the candles is almost the same. Let's see if we keep increasing the distance longer than 30 millimeter. You can see that because the left candle is too close to the stagnant area, so the downdraft is result in the flame jumping slowly. In the middle, the downdraft is more intense, and the interaction between the bundle of candles is more obvious. Even we will see the flame spray out. When the distance between the candles on the right is too long, the two oscillators will not be related. In the Schlieren photography below, you can see that the changes of the hot air is of opposite direction. We know that in-phase exists in the updraft area, and anti-phase exists in the downdraft area. So there should be a stagnant airflow between the in-phase and anti-phase area. In our experiment, you can see that the distance is the 25 to 27.5 millimeter. Because of the flame's airflow stagnance, the vibration of the candle flame will be inhibited reciprocally. For the Schlieren photography below, you can see that around the airflow to the candles is very stable, and you can see that the currents oscillate. So here comes to the conclusion. We use airflow to explain the phase-split bifurcation between the in-phase and anti-phase. And we know that the distance is less than 12.5 millimeters. It will show result in the updraft airflow. It will show the in-phase synchronization. As you can see in our observation experiment video, the flame is burning at the same direction, and the hot air changes around the candle even less. When the distance is longer than 30 millimeters, it will show results. Because of the downdraft, it will cause the anti-phase synchronization, and the period of the anti-phase synchronization is a little bit slighter than the in-phase synchronization. And we have also successfully found that there should be the stagnant airflow area between the in-phase and anti-phase synchronization. So our experimental observation is consistent with our speculations. Yes. So thanks for listening.
And then the opponent, you have 2 minutes to ask question to the reporter.
For the first question, so the two candle you only use each only one candle for each the two sides. You only use one candle.
No. In my experience setup, I suggest I use two candles as an oscillator.
Yes, I mean for each side you only.
I know. Each side I contains two candles, so I have two candles and two candles, two oscillators.
Oh, okay. And for page 8. Is that the graph? Is that the tracker graph or?
Yes, is that the tracker graph?
Okay.
Yes.
And then and also which part of the candle, the flame you check?
I check the top of the flame. Yes.
So you use the auto tracker or you check it by your?
I use the auto tracker. Because but I will see that if the flame will it's very intense and will have an eruption, right? So that I can't also
Okay, we will discuss it next. So how about on page 15?
Yes.
In here you talk about a regular beat. What do you mean?
Um, because in my experimental observation, my theory, so I think that the airflow between the candles is not very stable. So it will be cause the oscillation between the candle flames. And if the distance between the bundles of candles are too long, the airflows cannot quite influence each other. So I think that's I think that's because the distance is too long, the airflow can influence each other. So it will show that you have directly.
And opponent, you have 3 minutes operation.
可不可以给这个10或对是我觉得这个。我打下 airflow 这个我想稍微
那它会是哦，你是说他们那个他是用两束，哦。那它的图这样被遮蔽掉了，就跟狗一样。你可以攻击你把它做起来。就刚刚就那个。没有关系，有人说会射出这儿，让我们看一下。他说后面全是那种。可以投上去。现在可以吗？可以吗
Okay, and the opponent takes the floor.
Hello, every judges and competitors. I'm Rebounding Young from Changing Academy. Today I'm going to present problem 5, synchronized candle. And the problem statement I will not repeat again. And as the important part in the problem statement, it's also the oscillatory strength and coupled with other, and you will happen in phase or anti-phase synchronization. And also we need to investigate the distance. So to happen in phase or anti-phase, I think the flame cannot be regular, like the lighter or the never mind. And the synchronization will depend on the distance too. And for the summarizations of the reporter's report, for a problem statement, he pointed out the important part of the the experiment and know well what to do in this experiment. And also the series he do is to use the air force to cause, he think is the air force to cause the synchronization. Also, the experiment setup, he has sharing photography to prove his series. Also, conclusion is the air force caused the phenomenon happen. And for a reporter's report, he done a well observation video, also understanding the experiment well. Also, the recording video of experiment is clear, and the detailed variation have give us clear too, and also the results of the data is clear. Also, but the theoretical graph, no, there's lack of theoretical graph, and also explanation of the series. There is also error, so I think it's not enough. And this is what I'm going to discussion in the next part. And do you think how big the flame will affect the result of experiment? Also, what affect the most of the synchronization, radiation, convection, or the thermal diffusion? Also, explain your theory, not just the airflow, or do you have more theory of it? And also, where did you do your experiment? Is it in closed area or open area? Also, how did you do a tracker? And have you observed the mode that your anti-phase and in-phase happen together? Not just one happens. And will the two candles putting on the same side affect each other? I mean the two candles on each side. Yeah. And never mind for number 8. And have you identified a thermal line? I think it will affect the airflow. Okay, I want to go into this question.
You can go ahead.
So I want you to explain again how you do a tracker.
I do the tracker. So I use the tracker out. I use the tracker to track the top of the flame.
But you say you use the auto tracker. How did you do it? Because the color seems very same in that area. The auto tracker, I think, cannot track that same.
When I'm doing the experiment, it is very can do this.
So you check the breakout or the breakout part, or just the breakout part?
Breakouts.
Yes, the flame will break.
Erupt.
You say the flame will break when it is synchronized, right?
When the airflow between the candles is very intense, it will show the flame eruption. So when there is a flame eruption, the auto tracker will not be okay. It's just that when a candle is rising, I can auto track it. But when the flame erupts, I need to tap the screen.
Oh,
yes.
Okay. And so you think, how do you think how big the flame will affect the experiment?
How big the flame?
Yes, because you use two candles. How about three candles together, or only one candles together? Will it have the phenomenon happen?
Yes, in our Schlieren photography, we have shown that when there's only one candle burning, the hot air around the candle will be steady. And when there's more than two candles, I can see the more the candles, the more violent the vibration.
And also, except the airflow part of the theory, do you have other theory about it, or?
No, I just care for this.
And also, how about the thermal line?
What's again, sorry?
The next question. The line that is thermal.
It's thermal. Yes.
Do you have a graph of that? Do you have a?
No, sorry.
Oh, because for a thermal line, I think it can prove more about your airflow. Because for a thermal line, you can see the temperature around the flame, and you can know when the temperature around the flame can also prove the airflow around it.
So it means I can do more.
Yeah, I think it
Also, it will be better.
Yes.
Thank you.
And also, so you do it in an open area or a closed area? Or when you do the experiment?
I do the box like these
Oh.
these here. So
Oh.
maybe a little bit open area in the close.
So,
Yes.
so I think, so it's closed, right? It's closed, so you close.
How did you define the closed area?
Because if it is in open area, there will be external airflow too, so it might affect the.
But if we just put in there and there's a camera to observe the flame interaction. If we don't decide the kind of I think then it will not cause the flame eruption. Yes.
But I think when you're doing in the open area, the airflow in the environment still cause the.
So I do it in the like a chamber.
So do you minimize the effect of the airflow, the environment issue?
No. When I'm do the experiment, the environment airflow is very short. So.
Oh, okay, yes, thank you. And also, then
Yes.
for the sixth question, have you observed a mode that is two synchronization happens together?
Okay, so in my opinion, that's when there shows the in-phase synchronization, the phase difference will be equal to 0. And when there shows the anti-phase synchronization, the phase split is about 0.5. So I don't know why it can happen at the same time.
Okay, because for my own opinion, you can find the dead space too. So
Yes.
in my opinion, there is also a percentage that can happen. The two modes synchronization happens together.
So I don't quite understand your question, but I think that's when there is only one a plane like this, and so another candles another candles between the distance and the candle will depend the in-phase or anti-phase synchronization. So if they are the in-phase motion, the two will have the same. And if their distance is longer, it shows the anti-phase synchronization. It will be the irregular beat, not irregular, the opposite. The in-phase will is defined about the two candles. Yes, so
Okay, I understand.
yes.
And so when you use the candle, you use the same candle to burn for main experiment, or you change it because that's it.
Okay, so I use the same candle to when I done for the 12.5 millimeter flame synchronization, and I just keep increasing it, so I didn't change the flame. Because I think that's if we change the flame, the motion of the candle maybe will caused by we change the.
So you keep burning the same candle in your experiment?
Yes.
How about the height of the candle? Will it affect your experiment?
Okay, so. In the 20 millimeter. The 20 millimeter distance between the candles, you can see that the left candle is more larger than the right candle, right?
Yeah.
But actually, in my opinion, it won't cause the in-phase or anti-phase. Depend on the distance will different, because the airflow actually it will cause very large area. So I think that there is the flame amplitude larger is not related to this.
Okay. How about for another question? What do you think affect the most about the synchronization? The radiation or the convection or thermal diffusion?
Convection.
Can you explain?
So, in my opinion, the convection is more effect on the air value. So, I have set the I have this picture. So, this is when a candle is at have an airflow. So there is where there is no gravity. It will not have the thermal convection will not influence. So as you can see, the shape of the flame will be spherical. So if there is a thermal convection, the flame will be pointed. So I think that the thermal convection plays a most important role for the three things.
For my own opinion, I think the convection is just to take away the heat from the candle, and I think the radiation is the most important part of this experiment.
I think.
And also, can you tell me how you did the candle without the thermal?
Without gravity, sorry, I didn't find it. This is by the internet, so I didn't.
Okay. So for this experiment, have you identified an error in it?
Identify the error.
Yeah, may it happen an error. When you measure the distance, the error of it.
Error of it. I think that's because the airflow. So I think that's the airflow is causing will influence the large area. So I think the error of it. Yes, I didn't take the error, but I think that in my opinion, I think that will be pretty short.
I will end the discussion.
Okay. And opponent, you have 1 minute for summarize the discussion.
For the discussion, in my own opinion, I think the theory that it is lack of theory because the reporter just used airflow to explain the phenomenon. So I think he can improve it for next time. And also I think in the question of radiation and convection and the thermal diffusion, I think the radiation affect the experiment the most. And also, I have a question that I haven't talked about is about the wax of the candle. I think also the wax of the candle will affect the experiment too. And I finish.
Okay. The reviewer.
So now I have some short questions to the reporter and the opponent. So first, what takes the main cause of the in-phase and anti-phase?
In my opinion, I think it's in the Chilean photography, yes, you can see that I think it's the airflow more.
And what kind of airflow do you mean?
What kind of airflow? I think that's the thermal convection.
Okay, and what do you think
I think
is the main cause?
It's the airflow come down.
Okay, thank you. And second, how will you predict the period of the flickering when the distance goes even higher?
It means that
Distance between the candles becomes even higher.
no, it's just in this picture.
No. I mean, goes even higher because in your experiment you only get to 77 millimeters.
Yes,
even higher, like
if
100
we keep
millimeters.
increasing the distance, it will show the irregularity. Yes.
Okay, and what do you think?
And I agree specifically.
Okay, and third, will the one candle flicker by itself? Will one candle flicker by itself?
I think I think it is hard to do, but I think it's not.
Okay, and what do you think?
Yes, it will happen.
Okay, and please turn to page 12. The antiphase and page 11, please. You can see that the antiphase, and please turn to the antiphase. As we can see that the amplitude is not completely opposite. The amplitude here is not completely opposite.
It is a little, it's almost 0.5, right? When the left hand is the highest, the right hand is the lowest.
And do you think that this would be another phase, or do you think this is also the antiphase?
This is also the antiphase.
Okay, and what do you think about this question?
And yeah, I'll go also anti-phase too.
Okay, and fifth, will the distance, will one distance only corresponds to one oscillation? Only one phase? Will one distance only?
Yes, in this distance, like when the reach close to like 12.5 millimeter, it will be in phase and will not be the antiphase synchronization.
Okay, and what do you think?
And I think in some particular distance, it will happen anti-phase and in-phase together.
Okay, and how do you define the different phases? You define by what the different phases?
It means what can I see that different phases?
Yes.
In the in phase, the phase difference is close to 0. In the antiphase, the difference is
So you define by the period of the amplitude?
yeah, amplitude. The period of the two trajectory, yes.
Okay, and how do you think you should define the different phases?
By
Sorry, time is up. For review, you have 2 minutes for deliberation. Okay, review, please.
Honorable jurors and fellow competitors, I'm Kyle from Jinshen High School, and today I'll be a reviewer for problem 4, synchronized candles. Problem statement states that the oscillator flames can be observed when several candles burn next to each other. Two such oscillators, one can couple with each other, resulting in in-phase or anti-phase synchronization depending on the distance between the set of candles. And the key points we think is to find the distance and change the effect on the result, and what caused the candles to have different types of synchronization. So to a summary of the report, first is an understanding of the problem, to have a well-explained phenomenon of in-phase and anti-phase, and some theoretical analysis. They use a Schroderian analysis and the amplitude of the candles by the tracker, and experimental confirmation. They define the frequency and the distances, and they also provide the Schroderian graph. The merits of the reporter, First, he will explain the phenomenon and did shear analysis and clear analysis. For some possible next steps, there are some theoretical limits and further experiments of other parameters, and they do not have quantification. Fourth is they have too easy assumptions of the cost of in-phase and anti-phase. Fifth, they have no simulation of the vortex change. Six, no comparison between experimental data or theory data. And seven, they have a poor time management. And the summary of the opposition, some key sides of the opponent. First, they discuss about the situation that the candle flame is bigger, and they discuss between the radiation and the convection. And third is some experimental setup. The merits of the reporter, first, they pointing out some points that the reporters didn't describe well, and second, he also presents some of his own ideas. But some possible next steps, first, they could do more analysis on the configurations, and second, focus on what the reporter has presented, and third, a lack of focus on the experimental result. Fourth, more focus on the theoretical limitations. Fifth, discuss more about the airflow and vorticity. The reverse question, first, what is the main cause of in-phase and anti-phase? They both said about the airflow, but we think the main cause is about the vorticity and the toroidal vortex, also detachment of the toroidal vortex. And how will you predict the period of the flickering when the distance increase? And the reporter says irregular. And we think when the distance increase, the period also increase. And will one kind of flicker by itself? Reporter said no, opponent said yes. In our view, we think we must have a flickering because it's caused by buoyancy and density difference caused by the temperature difference. And in page 12, the anti-phase amplitude is not completely opposite. And why is that? The reporter just estimated and the opponent agreed with it, but we think you have to define the in-phase and anti-phase more accurately by the period. And each distance only corresponds to one mode of synchronization. Reporter said only one happened in once, and the opponent said they will have anti-phase or in-phase. And we think it must have an in-phase, anti-phase, and that phase all appear, or even the phase that transfers between in-phase to anti-phase. So the points discussed by them is the theory, and the reporter only responds to the Schlieren photograph. And we think you need to have more simulation by programming or vortex. And what is a closed area or open area? And next, what is the main factor leads to synchronization? And it's a thermal convection, and we think the heat release rate will also affect the result. Thank you.
Time is up. Reporter, please take the floor. You have 2 minutes for concluding remarks.
Here's my concluding remarks. So, why the candle phase will synchronize? So, because of the airflow, will let the two candle flames start to vibrate, and because of the airflow, there also will be the air buoyancy to let the flame up to a certain heat. So here's my concluding remarks for the question discussion. So did you only use one candle for two sides? I say that two candles in your bundles. Yes. So the second question will be, how did you track your candle flame? I use an auto tracking, and it is quite accurate. And did you conduct the experiment in a closed or open environment? And I say that in the closed environment. So another that the reviewers have said that because why will the sand, in my theory, I don't think that in a certain distance we can have the in phase and anti phase and dead phase. I don't think that because I said that the in phase exists in the updraft area, and the anti phase exists in the downdraft area. And the dead phase is the airflow to the stagnant area. So I think that in the certain distance, it should not be have the three motion of synchronized. Yes. So here's my concluding remark.
Okay. Any question from the jury? Professor Lee, please.
If there are three candles, so how will the pattern for three candles?
Yes.
Jordan.
If there is three candles, the blend oscillation will be more intense and the vibration will more strong. Yes.
And I think that there are four phases when they are oscillating with three candles, and in each distance there are also different kinds of possibility of which phase will have a higher possibility to oscillate. Yes.
And I think it will have three frequency happen, and also the frame is bigger and more easier to observe the phenomenon.
Okay. Please,
I have a question for the reporter. I just wonder, do you see the dead phase still have some oscillations?
Yes, because the airflow is not very stable that we can do so. In my you can see that there's also be some the amplitude of the plane will
I mean the dead phase.
yes,
Yeah, that's one.
the amplitude of the plane
Still some
will
oscillations.
like a little bit in phase, and in distance it's like a little bit anti-phase.
Yeah, but in
So-
your tables you see the almost zeros. You didn't write any the table you also calculation the dead phase right? You're in the conclusion in somewhere. In the conclusion or somewhere you have some tables to analyze all the data, right?
Yes,
This one, yeah,
yes.
it's almost zero, right? It didn't show anything.
Yeah,
The dead
because
phase
they-
area.
Yes, because they didn't synchronize, so they won't have the phase difference and they won't have the period.
But you already say also sometimes they have some anti-phase, right? The other one is also the in-phase.
Yeah, because
Yeah, I know, but the data seems like it still have some phase, not really the dead phase.
okay, sorry.
Yeah, I just means this one.
Thank you.
any question from jury?
Yeah.
Okay, please.
I just-
Let's go, please.
Yes, I just wondered, do you guys all the 3-1 know how can you explain it by the theory? By the theory. You say, oh, I think all three agree to use F4, right? Do you also try to looking for the theory?
Yes, we think that the near shear layer will cause the flow and the chordal vortex causing the flames to leach out.
Yeah, did you try to write down the calculation and all the parameters, all the things for equation? I mean the equations. I just need to know do you want you already challenge all the things, right?
Yeah.
But just I want the series, the data, series equation. Do you try looking for?
We tried to calculate before.
Yeah. Yeah. Yeah.
And we know we have to use the Boltzmann law, but we didn't have tried on it.
So I think that I have to try to find out the pressure utilization because first of all, this difficult is that it is a flow of air, so it's not really easy to yes. So and the second is the radiation is not the most important part in the experience. So I have tried to yes.
Yeah, could we switch to?
Can we help him to answer?
No.
So in our derivation, which we did in our report, we found out it is a density difference. In the final result, the frequency of the oscillating flames corresponds to the density difference between the air.
So, no further questions, and it's time for the scoring. And we show the score for the reporter. Seven, 8, 7, 6, 6, and 8. And we show score for the opponent. 6, 7, 7, 5, 4, and 7. And we show score for the review. 7, 8, 8, 7, 6, and 7. So, any comment from the jury for this problem? No? Then this fight is closed here. We have 10 minutes break. So each team, please take the position of the Okay. Ready? Please, reporter, please.
Hello, brothers and competitors. I'm Shinwen from Patricia Academy. And today I'm going to report about problem number 15, Rebounding Capsule. First problem statement. The thermal will drop on the hard surface whenever rebound to the release height, even if it had a natural spin. A capsule-shaped object, on the other hand, may exceed the initial height. Investigate the phenomenon. First of all, we find out some data that will be labeled. The initial spin thinks that the initial angular velocity was in the first situation, and the capsule shape on the definition is a three-dimensional geometric shape descending on a cylinder with vertical ends. As for the initial height, we actually give us some of our definition over here. This is one of the picture of our experiment. This is a trace of the capsule that we have observed at the initial height. We think that it could be the height where it will be released, or the height when the velocity will equal to 0 at the highest point. And these are the points that will be pointed out in our experiment. And this for the highest point over here to the bouncing over here will be the phenomenon we'll want to observe about. Now we got some resulting circumstances. This is the whole direction over here. And this is where the first of the circumstances about the instant velocity from the capsule to the floor. And these are the next two, and this is where the direction of the will be changed. The first reason is related to the relative velocity. And the other reason I think will be related to the contact angle, whether it changed or not. Let's start first the curve that we draw about. First of all is the direction of L. So that will change the omega over here, which equals to the velocity divided by r. And this is what we summarize of the sigma fx and fy. The sigma of fx equals to the friction over there, and the sigma of fy equals to the normal force minus mg. And here's our equation that we got about. So let's talk about the phenomenon. What will happen? We got actually simple theory about the conservation of energy. The gravitational force energy will turn into rotational energy or kinetic energy. The rotational one will change into the spin of the capsule, and kinetic will change to the vertical speed. And here is the equation over here. And at last the energy will become the initial sum minus the energy loss. The energy loss actually have 2 points to point out. One is the air drag, and the other one is the friction on when it contacts to the floor. So explain the phenomenon. We have turned it out to 3 cases when the contact angle between the x and the axle of the capsule itself, whether it is larger than 90 degrees, equal to 90 degrees, or less than 90. These 3 conditions actually affect the lower force over here. This will be less than the mg, the weight, the mass, and this will be the plating. As you can see, the total energy will be the rotational one added by the kinetic one. But in the 3 cases, we can see that in the middle, when the contact angle between the capsule and the floor is equal to 90 degrees, the angle will cannot have a change around the capsule, so every positive force will turn out into the velocity. So as our assumption, the closer the contact angle is to 90 degrees, the easier for it to observe the phenomenon. Alright, so here's our experiment. First of all, we use the test tube holder to hold up our capsule. Our capsule actually just put 2 compounds together. And the mass of it is 57.7 grams. And we put it together. And the tape is for the connection. And the test tube holder. Because during our experiments, we actually use the finger to take it out. So we use the test tube holder and to make sure that the As you can see, the track of the capsule is actually from the top point when we reach the first point. It got rebounds in the small range, but in the next motion, it will rebound in a higher range. And this is what we got result on our track. As for the velocity, we have changed it to x and y. As the velocity of the axle airplane, you can see that it has changed a little. And as the y function, it has changed from the positive to negative based on where it has become. As for velocity, maybe you should ask why would it have changed like right here over here. We assume that it's the friction of the kinetic to the floor has changed because it should be in a complete range like over here. But the friction and energy loss will cause it a new change. As for the acceleration, it should be 9.8 in our assumption. But the sparks over here is when it has the spark for the red line has crossed over here is when it will attach to the floor. And when we put out those crystals back here, the average of them is 10.2. It still has some, this is with 9.8, but it's really close over there. As for the angular velocity, this is what we have, but maybe we couldn't see what I have done with the relationship over here. So let's go to the next picture. This is another result of the tracker. As for the potential energy, we can see that around the highest point is mostly of the trace, and the kinetic one is mostly depends on the potential one. As the potential energy decreases, you can see that the kinetic one decreases. Now about the rotational one, I think we think that this is the most important point about the energy loss, because when rotational energy reaches the maximum, the kinetic energy and the potential energy will reach the minimum. And over here, when the rotational one just decreases over here, it can rebound to the higher points. And this is the sum of those energy together. The blue one is the potential one. The green one is the kinetic energy, and this one is the rotational energy. From the first chart, we can see that when the rotational energy has increased here, but some of all the energy have decreased largely. And in the second picture, we can actually see that when rotational energy has reached the highest point over here, the energy sum has been decreasing. But in other points, when the rotational one has decreased to almost zero, the sum of those energy has become even higher than the one before. And also, we got a result that it was have a slight rate of decreasing because of the energy loss in our assumption. As for our experiment, this is our setup, and we can see this is in slow motion. And we can see that the contact angle of the axle to the floor, this is one is much smaller than the other. This one is more likely to 90 degrees, so it can reflect in a higher way. Alright, so it comes to the orientation of relation, which means that how much can energy be consumed in the next motion. The equation over here is that the energy sum before and after, and then take the square root of it, and the one of the chart B. As when the sum of the energy has decreased over here, the COR had only become 7.98, and the sum of the other will become, when it had rotated over here, had become 9.96. And this is the chart we got from the square root energy sum ratio. And as you can see, the COR will become higher, closer to 1, when the angle is closer to 90 degrees. And when it is much smaller over here, it will become like 0.8 or 7 points, or 7.1. And here is our analysis or conclusion. We can see that the rotational energy will be the main reason of the energy loss. The rotational energy, as we can see in the lower picture, will be the most important reason of causing the sum of the energy to change. And despite the virus will happen by the contacting the floor and change the loss of the. As for the kinetic one, most of them we asserted is the relationship between it and the potential energy. When the potential energy decreases, the kinetic one will increase. As for the potential one, look how asserted changes over here to our that's the reason of the energy loss. One of the reasons is the air friction when it couldn't be the perfect for the object, and the other one will be the friction when it contacts to the floor. When it contacts to the floor, it might change the velocity of the axis or to decrease the total energy over here. And this is the end of the presentation.
Okay, thank you. So the owner, you have 2 minutes to express it to the reporter.
Okay, so thanks for the reporter's report. Could you turn to page 12? So how many times do you get in the graph? How many times rebound do you get?
The times of rebound over here is depends on over here is like 8 times.
So you track the whole motion?
Yeah, we did track the whole motion over here. And this is actually
Okay, so did you consider energy loss?
in our observation, we have to compare energy loss over here.
Okay, so you consider it, right? So do you
Yes.
have a graph that shows the energy loss versus the impacting angle?
Actually, we got the one for the total energy because when it had when we didn't got the energy loss, the total energy stay over here. So we can assume that's the
Okay.
in the sun.
Okay, so can you define coefficient of restitution again?
Alright, so the coefficient of the situation will be the ratio between the sum of the total energy before and after the rebounding.
So you define it as the energy change?
Yes, we've been defined as the rate.
Okay, so could you turn to page where is have the force diagram, the analyze of the force. I think it's page page 2. Yes. So do you consider the torque or no?
Yeah, we did consider the torque.
So do you assume so the real impacting point is this, and do you assume this to be the same to be a radius of it? Or
we actually assume the torque by the points between
Oh,
the
sorry. Time is up. Owner, you have 3 minutes for the preparation. Okay, opponent, please take the floor.
So hello everyone, I'm the opponent from Junior High School, and today I'm going to be the opponent of problem number 15, Rebounding Capsule. So this is a problem statement. It told that the spherical ball dropping onto a hard surface will never rebound to the release height, even if it has an initial speed. But a capsule-shaped object, for example the Tic Tac, on the other hand, may exceed to the initial height. What we're going to do is to investigate this phenomenon. So we think the key points is first, what caused the capsule to exceed to the initial height? Second, how the relevant parameters affect the rebounding height. So this is the reporter's outline. First, they give us some definition, like the capsule and how is the initial height and the initial speed that talks in the problem statement. And they move on to a theory talking about energy conservation and also gives us the force diagram and help us more understanding of how the force act on the capsule when impact on the hard surface. And they move on to a setup and they use two ping pong to create a capsule. And because this according to the definition, and they use some creative setup to control some parameters very well. And in their experimental data, they give us some angular velocity and angle versus the coefficient of restitution, also known as the COR, and also the energy loss. And in conclusion, they give us some energy transfer between impacting and what caused the higher height. So this reporter pros and cons. First, they give out a clear explanation of the definition and also a creative setup. We think it's very good. But there are some points that we think the reporters can fix. First, they didn't have the unclear percent of experimental result because we can see that their graph is so we cannot see very well. And second, 2D versus 3D. Is it reasonable to analyze 3D motion by 2D tracking? Because they use tracker to track the motion. However, tracker only can track 2D motion, but the capsule is actually the 3D motions. And last, they did not fix their theory model because in their experiment they also consider energy. In their theory, they consider energy concern. However, in real situations, there must be energy loss, maybe depending on angular velocity or depending on the COR, and they didn't told us. And last, they need to have more discussion on the experimental data. And this some Q&A I have asked for the reporter first. Do you consider energy loss? Reporter answered yes, the total energy graph. And I asked for a definition of COR, and the reporter answer is the rules of energy before and after rebound. At this point, we will be discussed in the next part. And third, did you consider the torque? The reporter answered yes, because in our opponent's view, the torque caused a very significant impact of the impacting angular velocity. And last, how many times recorded rebound? 8 times with whole motion, because we have to measure their data. And what we are going to add is first about theory. And we will first talk about the analysis of body diagram, and also known as the force diagram, and why will the capsule spin faster after rebounding. And definition of COR. Also, the problem statement told us the spherical will never release the initial height. So why? The reporter didn't talk about, so we will discuss that later also. And next, question about result. How can you do for a comparison of experimental data and the theory, and adding corrective factor or not? And what situation caused the higher rebound? Is there a critical angle or not? And question about experiment, including the 3D motions and and how to track the angle the capsule hits upon the ground. So we can start a discussion.
Okay, please go ahead.
Okay, so can you turn to page 2, the force diagram. Oh yes. So can you briefly explain why how the normal force and friction force act on the capsule? What caused the effect?
In our assumption, we think that the normal force, first of all, the normal force will be caused by the energy over here and by the
What over here?
yeah, we'll assume that the energy point will be mass over here, and the L over here will also cause the normal force to change because of this will cause another force energy.
So do you think the normal force and friction force will actually cause a torque? Can you agree with me? Will cause a torque in the center of the capsule. Can you agree with me?
Yeah.
So do you think this torque plays a great role of the impacting?
In our assumption, we think that the torque over here, it should be a point points and over here.
So you think this line is important?
I think that this line over here from over here will affect the one over here. This one is the one affecting the spinning of the capsule itself. So when it was in the same side over here, it was actually decrease the affection of the omega over here.
Okay, so I can show you my stuff. So first, if this is a capsule-like object, okay, so you consider this as your radius r, or
Actually, in our radius, we consider
this one.
Yes, we put the angle.
Okay, so you consider this one as an r. So okay, so next, so the normal force and friction. Okay, so normal force and friction force will also act on the capsule. So it will actually cause the center of mass a torque, right?
Yes.
So we know that the torque will actually cause the inertia of the moment 2 times the acceleration of angle. So in my opinion, the torque plays a very great role because the torque can be described as the normal force times the distance between center
The center point and the
center of mass and the impact point. Yes, and also the friction force. However, the friction force and normal force have a different direction of the torque. One is a clockwise and one is a counterclockwise. See, so if we define the if we define the clockwise as a positive and the counterclockwise will be a negative. So the Fs will cause a negative torque. So we need to minus it and this y. And in my opinion, I think it will cause an angular acceleration. And I think this is the main cause of why the capsule will spin faster after rebounding. So what is your idea?
My idea is that we have taken into account the equations like one show over here when related velocity has changed, the way of the friction will have changed. So
Yes.
this is why we think that it will be rebounding in a faster and slower way. And this when they have to carry in this direction, well omega will be over here.
Yes.
We think that we will become slower.
Because
And the other point of view, when it comes to another point, will be better slower. Depends on when
The normal force and friction force depends on.
the relative velocity over here.
Okay.
It depends on the way of the friction.
Okay, I got it. Okay, we move on to the next question. So, so Matt, what is the definition of you define it as the energy after the impact and before the impact, right?
Yes.
Okay, at this point, so you can see, so energy after impact is you write mg times the height. So your energy after and before can describe as the velocity before the impact and after the impact, right?
Actually, it's not the point of view of the
Center velocity, or because this will equal to this, right? Square. Oh yes, the square. Yes, the square. So in my opinion, I think the definition of the definition of COR needs to be fixed because I think the definition of COR is if it is a capsule and it is the impacting point. My definition of COR is the impacting point velocity versus the moments of the rebounding impacting velocity, which also means that this point. So if we assume the capsule have a center of the speed v, center of velocity v. So we know that we need to calculate for this impacting point, right?
So do you think that the tracking point of ours should be the impacting point of our capsule store?
Yes, yes.
In our experiments, we actually have the tracking points over here.
No,
So in our
it's not a tracking point problem. It's the definition of coefficient of restitution because the coefficient of restitution is defined as the different velocity, impact, and after impact. So I think I think we need to focus on the impacting point of the COR. So in my okay, so yes.
Also, in our relationship between these, our data was were actually from the data we get is from the tracking points.
Yes.
So do you think that we found a problem about the tracking points and
No, I think it's a small difference of the small problems of the definition of coefficient restitution. I will explain my thoughts. Okay, so yes. So we know if the center velocity is v, and we know if the impacting point is va, so we know that the center of mass velocity will equals to va plus r omega, which omega is the angular velocity of the capsule. Because they are relative velocity. So actually the impacting point is be written like v minus r omega. So I think this is the definition of the yes. Yes. So do you agree with me?
So the point that we should think is that we make it as the center of the velocity.
Okay, so we can move on.
This should be the point that we should take in the later.
Okay, so thank you. So next about some other results. So you have a comparison between. Do you have a comparison between experimental data and their theory?
Actually, in our experimental data, it showed that the energy loss should be less than the one we got in our experiments.
Yes.
Because of few reasons, their drag and friction.
Okay, so can you estimate? So if today rebound, so today impacting angle is 70 degrees. So can you estimate the energy loss of the angle?
It means that we got to estimate the energy loss when the contact angle is.
Yes.
We haven't done that in our experiments, but
Okay.
we assume that we can change the contact angle and the velocity loss by changing the height when we release the capsule.
Okay. So in my view, I think the energy loss needs to be added for the correction factor. So if we can find the impacting angle and how it will affect the energy loss, I think it will be a correction factor for the energy loss. Can you agree with me?
Yes, we think that the correcting factor will be the ones we have to consider. One of the is of course the friction of the flow.
Okay.
Another one is that in our experiments we used to use the finish duplicate out of it instead of just releasing and
Okay, I got your point. So and next, I want to talk about is how do you think about why the spherical ball won't rebound to the initial height? Why? Because you haven't presented it in your presentation. So why do you think it?
in our assumption we think that R will be a great reason of it because in the capsule shape the R over here will be much bigger than the one of the radius of the boat itself. So we think that the distance between the middle of the capsule and the over here the points will be a good reason.
So it's okay. So in my view, I think why the spherical ball won't rebound to initial height is because of the coefficient of restitution. It won't always bigger than 1. So there is actually an energy loss. But for the capsule, there is actually 2 force act on the capsule and for the ball. Okay, thank you. So for a concluding
1 minute for some.
Okay, so for concluding remark, first we talk about the analysis of the force diagram because we think that if the force diagram can help us have a better understanding of what parameters cause the capsule to spin faster, and also we fix the definition of coefficient of restitution because the COR is defined as an impacting point, and we actually fix some theory mistake, and we talk about the results between the data and the theory. Maybe we can do some experiment of how the energy loss depending on angle. So maybe we can add a correction factor for the future plane. And for the last, we talk about the spherical object and versus the capsule. So in my view, the capsule will bounce higher than initial height is because of the torque caused by the normal force and the friction force. However, for the bow, just the bow, the friction force, the normal force acts on the center of mass, so won't pull the torque. Thank you.
Okay, review the next question to the author and opponent, please.
So thanks the recording presentation. There are important two questions. So my first question will right, please. And please, it shows it shows that two types of contacting angle in which their angular velocity is the same, like in the baseball. So in your opinion, think which capsule it will be bound higher? Which capsule?
In our opinion, first of all, it's the related velocity over here. When it will be the same side of the will become the related velocity here will first become higher.
So you think the left or that capsule will be nice?
First of all is this one. And the other one, when the contact angle here, because the contact angle wouldn't change so much when the direction of didn't change. So we can assume that in this situation it will
Okay, I
be
understand.
higher.
So what's your opinion? Which capsule will be bound higher?
I think it depends on how the friction force and normal force act on the capsule, because normal force will actually cause the same direction every time. However, friction force will change the direction depending on the omega of the angular velocity of the capsule. So it depends on the normal force and the friction force cause the torque.
Yeah, I understand. So the next question would be when the capsule contact the surface, do you think it is the static friction or kinetic friction?
I think that the friction there will be kinetic because first of all it's not the
Yes, okay, I understand. So what do you think?
I agree with her on that friction.
So in the page 10, it shows that your capsule is a ping pong ball. So do you think that it is appropriate for the
experiments? Can we go to the
no, just think it is appropriate. Do you think?
over here we got some comparing between the capsule and the ping pong balls. Our assumption we see that ping pong ball, first of all,
What do you think of the ping pong ball is appropriate? Is yes or not?
yes, we think it is.
So what do you think?
I think it depends on your definition of the capsule.
Because the problem seems that it is a
Yeah. So I think the ping pong is actually applicable. Yes, it is.
Okay, so our first question will be on the page 11. And it seems to be a z-axis display, and did you think it should be taken into the consideration? 11, please. There should be a z-axis displays. Do you think it should be taken into consideration?
In our experiments over here, we got over here, and the ping pong ball will be when it's straightforward over here.
Sorry,
I think VX will be a fact.
understand.
In our experiment setup, we actually try to minimize the effect of the other one because then
Time is up. So review 2 minutes to prepare the concluding. please take the floor.
Honorable judges and fellow competitors, I'm the reviewer from Team Google. So here's the problem statement. And the reporter and the opponent have discussed about it, so I will tell you. So here comes the summary and comment of the report. So in the phenomenon of the report, it says that a capsule-shaped object rebound height may exceed its initial height. And loss of height to torque, conservation of energy, and COR. The changing factor, the report only do is the different rebounding circumstances. And setup is the two ping pong balls connected together, and also the camera. The result is the correlation between contact angle and angular velocity is the main factor for the capsule to rebound and exceed its initial height. Rotational energy is the main reason for the energy loss. Rotation energy is related to the contact angle. So some advantage and suggestion for the report is that many diagrams consider energy loss in graphs of the motion to clearly see the rebound. And the suggestion is lack of the parameters and maybe louder voice that we can heard. So here comes the summary and comment of the opponent. The opponent have very good advantage that many details about the experimental theory are considered and asks about many conditions and clear summary of the report's work. But I think that we should more dig out about with the report and sorry. So here comes the summary and the discussion. So opponent asked the reporter that, did you consider energy loss? The reporter answered, yes, we consider energy loss. And in my opinion, if we consider energy loss, we can more accurately explain the observation and have a more completely theory. The second question will be, how does the normal force and friction force affect the motion of the capsule? The reporter answered not unclear answers. In the reviewer's opinion, I think that equal cursive torque on the capsule and affect the motion of the capsule. So here comes to the conclusions. The conclusions are in the base point of the report is that the moment of inertia should be considered, and the tracking point should also be mentioned about it. And camera angle can also be considered to calibrate the height. My question for the reporter and the opponent is that it's the friction connected friction, or static friction at the contact point. And the reporter and the opponent also answered the connected friction. So I all agree with them. The second question would be, did you think you can use two ping pong balls as a capsule? And the reporter answered yes, it's probably possible. The opponent answered yes too. But we think the definition of a capsule is a cylinder with two hemispheraces connected on both ends. So the problem statement I talked about, maybe the techniques will be better on doing the experiments. So this is the end of my report. Thank you.
So reporter, please take the floor. You have 2 minutes for the concluding remarks.
Alright, thanks to the opponent and the reviewer. And here are our concluding remarks over here. First of all is the question asked by the opponents. So why do the tracker tracks minimize the motion? The answer is that we can minimize the effect by using the experiment data. Later, however, for the friction force will act on the motion. And we assume that sometimes we will be making the motion index lower, and sometimes it will have positive or negative effects during the motion. And we had a discussion about the definition of CR, and we got the results of maybe we have to change the time points over here because we got our results by the so we can fix that in our later experiments. So we have to consider the energy loss in our experiments, but we got the experiment data because when it didn't consider the energy change, it should be a static point. But we still can have it done in an idle state, so maybe we can have some simulation done in the later experiments. And here we going to have some experiments in the definition of CR as what the opponents have said. And the contact angle changing will be another point which will be considered in the later definition. We assume that we can change it by the height of the point of releasing. So it can be the later point that we can check on the extinguished points. Also we consider friction and friction but not static one, while the capsule was actually moving straight forward. your plate contact friction whenever through. And as for the capsule shape, which the reviewer had asked for question, I think we can depend on the states over here. Because the capsule shape actually got a little bit different. Alright, thank you. This is my annual report.
Okay. So any question for the jury? So no question. Professor, please.
I have a question for all three of you. So according to the problem, so can you answer me why a spherical ball would never rebound to the release hub?
Another assumption is because of how it has caused in the cylinder shape. Because it got an extra point of R, a bit bigger and have a greater direction of power.
So can I draw some diagram on the
Can you use a simple sentence?
Oh, okay. It's like for the spherical ball, when it bounces on the hard surface, it has the normal force and the friction force. However, friction force won't have any component that will cause the y direction velocity to be bigger. However, for the capsule, there is actually normal force and a friction force, and the friction force will actually cause and normal force and friction force. And for the y direction velocity, there is actually r omega will need to be considered. So for the y direction, y omega velocity should be considered. So this means that the capsule-like object will have a bigger incoming velocity than the same situations of spherical ball. This means the greater impact height will be.
So in my opinion is that because the force contact point won't hit the torque, so the energy won't transfer.
So I have another small question for you guys, all three. According to the problem, it says a capsule-shaped object can exceed the initial height. But I didn't see anything from your report, and I didn't see anything from your discussion. 有它超过原来的高度。
Alright, in our presentation we have mentioned that we will consider the initial height as the highest point in the later one rebounding. So when it has rebounded to the next point, it might have a rebouncing on the higher points. So we'll consider it this point before rebounding to later as the initial point, as the initial height in our experiment.
Okay, so for the opponents, we see if in the condition that need to reach the initial height is that depending on the angular velocity and also the center of mass velocity after impacting. Because when the angular velocity is bigger, we know that the height of the capsule will become lower. But maybe not, because we need to also consider the kinetic movement, the center of mass velocity. So I think when you need to exceed the initial height or even higher, it depends on the angular velocity after the impact and also the velocity of the center of mass after the impact.
Okay, so in our opinion, in our experiment, that when the capsule is first down to the ground, and the first hit is, we call that is the initial hit, and the second bounce will upper than the initial hit. So we use that the first rebound is the first initial hit.
Okay, any questions? No? Then it's time for the scoring for the jury. Okay. Now we show the score for the reporter. Seven, 6, 5, 6, and 6. Now we show score for the opponent. 8, 8, 7, 8, 6, and 7. Thank you. Now we show score for the review. 7, 7, 7, 6, 6, and 7. So any comment from the jury? No comments? Then, this fight is closed here, and we have 10 minutes break. So each team please take the position for the next step, next fight. So thank you. Please change properly to the reporter. You have 1 minute.
Okay, I would like to challenge problem 12, global force pendulum.
So each team please write down the name of the representative on the board. Please take the floor.
So honorable judges, fellow competitors, good morning. So today I'm the reporter from Chinchon High School, and today I'm going to be the reporter of problem 12, we will post tangles. So next, first look at our line. First, we will begin with our problem statement, move on to a video and a theory and an experimental setup, and also result in some discussion about the experimental data and also the conclusion. So problem statement told us the wave-rotor pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down, base and rotate about its vertical axis. What we are going to do is to investigate the behavior of such a pendulum and how it depends on relevant parameters. So this is our observation video. On the left video, you can see as the pendulum moves up and down, the rotational speed will actually be affected. And on the right side is a vertical one. So this is our theory. First, we separate our theory into two parts, the vertical one and the rotational one, which means the z direction and the theta angle. So what we are going to do next is to apply Lagrangian. So the definition of Lagrangian is the total kinetic energy minus the total potential energy. So we try to calculate for the total kinetic energy. First, the vertical one can be expressed as the half times the mass times the square of z dots means the vertical velocity, and the rotation one is also the same. So for potential energy, the vertical one can be expressed as the half times the k means the spring constant, and z means the direction of the z direction. And also we need to add the coupling term because this system is actually coupling. So what is coupling system? I will explain later. So why do we apply coupling term? So the definition of coupling is if two systems can transfer energy to each other, meaning they having an interaction to each other. So from the observation video, you can see that the rotational speed will actually change with the time, means that the energy is actually transferred between the rotation one and the vertical one. So we need to add a coupling term written as this, and this term accounts for the fact that the energy in the z direction is dependent on the energy in the theta direction, and the coupling term is actually a kind of potential. So we add it to the Lagrangian. The definition of Lagrangian means the total kinetic energy minus the total potential energy. And from Euler's equation, we can finally solve the equation of motion, can be simplified as this. And by solving these two terms, we can find the general solution of this system. So in order to solve this equation, we assume the system to be a normal. So what is a normal? I will explain later as well. So the mass can oscillate with the same frequencies and phase angle, but with different amplitude, and this is the definition of the normal. Therefore, we assume the solution will be like this. So what is the normal of this system? First, the frequency of rotation forced by the inertia of the mass matches the natural frequency of the system. This means the first normal frequencies. However, in this system, there are actually two normal frequencies. Second frequency is of the rotation of the mass opposed to the natural frequencies of the system. So after calculating, we set k over n as the square of omega z, del over I as the omega theta. So we can simplify our equation to here. So in order to find the solution of A1 and A2, we apply the second order determinant equals to 0. And finally, solve the omega 1, the square root of omega 1 and the square root of omega 2 means the frequencies of two normal modes. So only when the frequencies of oscillation of the mass is equal to natural frequency in z and theta direction can we observe the system to oscillate in the normal mode. So we make a substitution that the omega z and omega theta equals the natural frequency we define as omega. So we calculate simplified equation to here. So we also define what is the beat frequencies, means that the square root of omega 1 minus the square root of omega 2 equals this term. So after combining the above equation, and we can finally solve A1 and A2 over the ratio of A2 over A1. And finally, after some calculating for the first mode amplitude and the second mode amplitude, and by combining the linear combination of its normal mode, we can get z of t and theta of t motion. And we need to apply for the initial condition, which we assume that the z of 0 means equals to z naught, and the theta of 0 equals to theta naught. This means the initial velocity of vertical one and the rotation one is equals to 0. So therefore, we can find the general solution of this motion of the Weber-Fuchs pendulum can be expressed as this, which z of t and theta of t all have the roots of n over I, and also be affected by the omega 1 and omega 2 with the nature, which means the two frequencies of normal mode. So these are experimental setup. First, we find a helical spring and attach the pendulum, and we attach the cotton thread to tighten this, and use scissors to cut it down in order to make sure that the pendulum moves up and down directly and without the spin. So we use two camera mounts, one for the down one and one for the horizontal one. So these are parameters go. First, we need to compare between pulling down and pushing up pendulum, and we change different elongation, and we find normal modes of the oscillation and theory line. So this is a background known value of the spring and the pendulum of our experiment. So in order to find the frequencies of two normal modes, we apply MATLAB FFT, and this code is written by ourselves. So why do we use FFT? FFT stands for the fast Fourier transform, means we can convert a signal from its original domain over time or space, which means also means that our system, because we will track the motion of z and theta with the time, so it's actually a signal from its original domain, which is time, and to a representation in the frequency domain. So we can find the characteristic frequency of a signal and obtain omega 1 omega 2 by equals 2 times pi times f. Okay, so first we push out 35 centimeters from the balance point. So this is the FFT of the experimental data. We can find there's a two peak, means there are actually the two normal frequencies, which is the same as our assumption in our theory. So characteristic frequencies of two modes, we can find the normal oscillation mode of these two. So we plot the experimental data versus the theory line. So we can see that the theory line really matches the experimental data. However, in our experimental data, there is actually a decay, and we will explain why it will be a decay. So this is Z of T experimental data. So what impressed us is there's only one peak of the experimental data, meaning there's only one characteristic frequencies. This really impressed us because in our theory model we consider two normal modes, and second biggest amplitude is lower than the characteristic one. So we need to do in the following presentation. I will talk about why will it only have one normal frequencies. We'll discuss that later. So this is the experimental restored compared to the theory line. We can see that it really matches as well. However, the experimental data will present a decay as well. So this Z of T plus theta of T, we can see that the bigger radius, the smaller moving distance of the pendulum will be that circled by the blue. And so we can so our assumption of the transfer energy between rotation one and the vertical one is accepted. So next, we do the experiment of going down 30 centimeters. So as well, we do the theta of T experimental data, and we find the same normal oscillation modes of the previous data. So why would it be the same? So from the previous theory, we see that the square root of omega 1 and the square root of omega 2 only depends on least relevance of omega z, omega theta, as well, which means the common constants, and n, the mass of the pendulum, and also the I. So it didn't matter the elongations. So this experimental result compared to a theory line is also has an experimental decay, and it fits very well. And this DLT experimental data also only have one characteristic frequencies. and this experimental result coming to a serial line also has an exponential decay. So first, so this is the other plot, and we can see the same trend for this elongation. So discussion one, why did the experimental data present decay? So in our model, air resistance is not considered. However, in real situations, air resistance plays a great role, which affects results very much. So we must fix our model. So in this direction, the air resistance can be written like this. So our system applies Lagrangian. So actually, we need to turn our air resistance to a generalized force, so we can apply to a Lagrangian. So we change to a generalized force written by this, and we assign the B as a low times C times A. And after solving the equation, we can finally find the simplification of V of t and C of t, and both times the exponential decay. So it actually matches our real situations. And next, discussion two, why is our experimental data of V of t only having one characteristic frequencies? So in our observation, because our spring is too long, about 2 meters at the equilibrium point, means the balance point is not the real, it's too long. So in our observation, the spring will divide it into 2 upper and lower sections to oscillate separately. You can see at the left right chart, the up have the density and the down have the density, and means this doesn't oscillate at the same time because it's too long, so only have one frequency. So by solving that, we're using shorter spring, and we finally correctly find 2 normal frequencies. So our discussion is really correct. So we only find one normal frequency, which we seriously didn't consider. So one situation only occurs one normal frequency. We are curious. So we consider the theta naught at 0 in our previous presentation. However, we turn theta naught into 90 degrees, and we only find one peak being only one characteristic frequencies, and also the negative of 90 degrees. So we make our conclusion. Our model is applicable. However, under the condition of short length of spring, so we can make sure that the spring oscillates at the same time. Second, there are 2 situations that only have one normal frequencies for a fixed length. First, when the theta equals to the 90 degrees or the negative 90 degrees. And third, we still need to add correction term, which is the exponential decay, in the general solution of our theory, because there's actually the air resistance plays a very great role in our system. Number 4, for long spring, Z of t oscillation mode will be affected by the separated oscillation of upper and lower spring. So these are references. Thank you.
Okay. So the opponent will ask question to the reporter. 2 minutes.
Honorable judges and fellow contestants, I'm the opponent for number 12 Google Plus Penny. So first for some short questions. So can you turn to the page where you have your spring constants, the specifications of your spring?
This one?
Yes. Okay. So how do you measure the spring constants for both the longitudinal and also the torsion?
Okay, so first for the line for the spring, we use a weight meter to find the F equals the K times X. And for the torsion constant, we apply in our theory to find the torsion constant.
So the torsion constant is derived from your theory?
Yeah, it's derived from our theory.
Okay. And also the other thing is that how do you calculate your coupled constant?
Well, what do you mean? Using omega 1 and omega 2?
No, the coupled constant for the
coupled constant is also applied in our theory to find.
Okay, so for both the torsion constant and the coupled constant, you derived it from your theory?
Yes.
Okay, thank you. And okay, so for the pendulum, can you tell me how did you create this pendulum?
I just go to our experiment lab and find a.
Okay, can you show me the video?
Your video?
Yeah, the
okay.
video.
So, this one?
Yeah. So can you quickly tell me about how did you create this?
Create this pendulum.
Yes.
Okay, so basically we go to buy two long screw and there's a 2 bigger weights in order to create the waveform panel, because we have searched for some references that told us that this type of panel will be have a visible effect.
So it has a better observation.
Yes.
And how do you connect it to? Did you connect it to your ceiling, because I can't really see it?
Yeah. We connect at the top of the
fan here. So because our spring is too long, about 2 meters. So in our second experiment, we just do in our
Okay,
like
time
a
is up.
table.
Thank you.
Thank you.
So, opponent, 3 minutes for preparation. Okay for you?
I'll wait for the clock. Okay, I can start my presentation.
Okay, opponent, please take the floor.
Okay, fellow contestants and honorable judges, I am the opponent for problem number 12, Wilberforce pendulum. And here's the problem statement. So the most important thing in the problem statement is investigating the phenomenon that the mass can move both up and down and also rotate about its vertical axis, and how these two motions interact with each other. And also, how these two motions will depend on the relevant parameters, which may be related to the spring and also the mass. Okay, and here's my outline and summary of the reporter's presentation. So for the phenomenon, it is similar to the problem statement. The mass can both move up and down and also rotate about its vertical axis. And they, for the theory and laws, they use the Lagrangian, and also they use the fast Fourier transform, and they use Python to run their data. And for their setup, they used a helical spring, which is, I think was about 2 meters, and they found a pendulum in their laboratory, and also scissors to cut the spring, and to make sure that that the Wilberforce pendulum would only go up and down. And also the cameras to shoot both the rotational movement and also the longitudinal movement. And so for the parameters, the reporter changed the different displacement of the longitudinal movement to observe different phenomena of the Wilberforce pendulum. And for the result and conclusion that the model is applicable under the condition of a shortened length of the spring, which they got from the theory and also a combination of their experiments. And here's my comment for the reporter's presentation. So I think it was a good presentation. There are many theories and I think it was pretty clear. And also, he compared his experiment and his theory. He showed his data and also his theoretical fitting line. So I think that was a really good point. But a suggestion I would suggest to the reporter is that maybe more videos of the Wilberforce pendulum can be shown inside of his presentation, so we can see different types of phenomena and understand more about the Wilberforce pendulum. And next are some of my questions for discussion that I will be asking in the discussion portion. So for the theory, I saw that there was an assumption made that both the natural frequencies need to be equal, which is the longitudinal frequency and also the rotational frequency, the natural frequency, they need to be the same. And I want to understand more about this in the discussion. And also another important thing that I would like to ask is the main reason of energy transfer. How does the energy transfer between the two modes, longitudinal and also the rotational? Okay, and next for the setup, for the experiment and setup. What is the purpose of pulling down the spring as a parameter? And the next is the conclusion where he talked about the normal mode. Okay, and I would like to start one.
We can go forward for the next step.
Thank you.
Okay.
So let's first start out with how the energy transfers between the two modes.
You mean the theory part?
No, my question is, there's a longitudinal movement and a rotational movement on the screen. So how does the energy transfer from longitudinal to rotational and from rotational to longitudinal?
So I think it's the main reason. So in our real estate, because we apply the coupling term, so I think it's because of a couple.
Okay, so you think it's because of
Yeah, yes.
I think that it might be related to the spring's structure. So when you're pulling down, it might uncoil or recoil, depending on how you pull or push up. So that will create a torque on the mass and it will start to rotate.
In our experience, we only the last two graphs we turn the 90 degrees, and in the previous data we didn't have any rotation, the rotation.
Okay. Yeah, I understand your what you're saying. So what I'm saying is when you rotate, there will also be a slight longitudinal displacement caused, and this is because of the spring structure. Do you agree with this?
You say the spring structure?
Yes, because it's a helical spring.
I agree.
Yes. So I think that will affect the energy transfer. Do you think this is correct?
It will actually affect. So yes.
Okay. So and it will also relate to the coupling constant, which you mentioned earlier.
But yes. So but in our theory we have considered. But in our theory, we only consider the ideal model. So I think if the helical spring really have like you mentioned, the spring, and I think we need to maybe a little fix on this motion.
Oh, okay. Because if the spring wasn't helical, it would just move up and down, and it wouldn't cause any.
Yes.
Okay. And another thing I would like to ask. So there was an assumption made in your theory that the natural frequencies, both the longitudinal and the rotational, should be the same.
This one?
Yes.
Okay, so.
Can you explain more about this?
Okay, so because because this is our theory assumption, so we assume it will be a normal of our theory. So normal means the omega z and omega theta will the omega z is k over n and the omega theta is a del over I, meaning the rotation one and the vertical one. So if both vertical one and rotation one matches the natural frequencies, meaning they have the same frequencies, then our normal can be applicable. So
Okay.
that's why we substitute.
Can you show me how did you calculate the natural frequencies of the longitudinal and also the rotational movement?
How do I calculate it?
Yes.
In
The
our
natural frequencies.
experimental data? Or
From your experiment, from your setup. Because you need to put your spring constant and also the mass of the pendulum to calculate the natural frequency.
Okay, I know what you mean. But in our experimental data, we only plot the z of t and theta of t of our motion model, and this didn't have any natural frequencies, only omega 1 and omega 2.
Okay, but the normal frequencies are affected by the natural frequencies.
Yes.
So can you show me how did you calculate your natural frequencies?
So for our So I calculate, okay. So simple, okay, so I know. So we have tests for the mass of the spring and also the spring constant. So we calculate for the n over k, the root of n over k, and we find the omega of
The omega z. Okay.
Yes,
and
yes.
how did you calculate for the omega k?
Oh, also I make sure the torsion constant is I put in our model to find it, because there are actually some equation we can find too. We can find the some equation we can find the torsion constant. So in the inertia of the moment we calculate by we creating a slope and putting the pendulum on the top and let it roll down, and we calculate for the inertia of the moment, because our pendulum is not too easy to just calculate by the mass. Yes.
So it seems that you made your assumption and then you calculated the natural frequency.
Yes.
Then how can you be sure that the natural frequencies were the same to begin with?
So in our assumption, we assume this will be the same. So in our calculation, it's actually not the same. The omega.
Then the assumption would be wrong.
Yes, would be wrong. So
then you can then the theory it might differ from what you wrote down in your slides.
So there will cause a little slightly difference of the when the pendulum keeps moving. There will cause a slightly difference.
And did you do a correction to this experiment?
Oh, I didn't.
To the theory.
I didn't do it. I only do the correction term of the air resistance. So this maybe we can improve next time.
Okay. Next let's talk more about. Can you turn to the page 7?
7. Okay.
Yes.
This one.
7. Yes. Okay. So the z of t here. So the z of t here and the theta of t here. Are they already coupled together? Is this movement the coupled motion, or only the motion they would do if they were independent?
Okay, so the reason we assume this solution is because we need to solve this ODE.
Okay, so this is your assumption.
Yes, because we consider it as a normal, and a normal definition is the same frequencies and a different amplitude. So it stands for A1 and A2. Yes.
So next, from your theory, it seems that you can find the general solution of motion for the
yes,
Yes, this is the general solution.
Yes.
Okay, so how would you create a normal mode? So how would you control the initial conditions such that you could only observe a normal frequency?
So in our experiment, we didn't change the inertial moment.
Sorry. The initial conditions. Sorry.
Initial. You mean? Okay, so.
Longitudinal displacement.
Okay, so in our last paragraph, we are shown we have do when the rotation have when have 90 degrees and it's only have one normal mode. And however, for our experiment, we find two normal modes because we do the FFT analysis, and this means and the initial condition is theta naught equals 0.
Theta naught equals 0.
Yeah, so theta naught equals 90 degrees, and negative or 90 degrees will only have one normal mode.
Okay. Yes. So can you please turn back to the general solution?
Okay.
Okay, so you mentioned here that if theta naught equals 0, that there will only be one normal frequency. Is that correct?
Equals 90 degrees.
90 degrees.
And negative of 90 degrees.
So only this initial condition.
It depends. Okay, so it depends on how we push down or push up. So there, yes, only 90 degrees. We see there's only 90 degrees.
Because I think that there is also if you need to create this initial condition, there needs to be I think a ratio between the longitudinal and also the rotational to create the initial conditions for a normal frequency. Is that correct?
So you're saying we need to change both at the same time?
Yes, I think both of them need to be changed.
So
here's my reason.
yeah, okay.
Because if there was only one normal, I believe one of the amplitudes would be 0. Is that correct?
Yes.
Yes. So
almost 0.
Almost 0. Yes, because there is experiment.
Slightly.
Okay. So then you need. So if we look at our amplitude here, there needs to be a ratio of the square root of m over I between the theta 0 and also the z 0. So you agree with this thing?
Yes, I agree with
Okay. And so did you also use this ratio of the mass and inertia to calculate the initial conditions that you need to do to observe the normal mode.
Okay, so in our experiment, we have the same M and have the same inertial moment. So maybe in our future work we can change this because if we change the mass of the pendulum, we will also change the inertial moment.
Okay.
So we can control these two, one change and the other two change.
Okay.
So we can do it.
Can you turn to your fast Fourier transform?
Fast Fourier transform. In code or
Not the code.
This one?
The data.
data. V of T or theta.
This one is.
Okay.
As you can see here, there are two spikes, right?
Yeah, two spikes.
Okay, so these would be the normal frequency.
Yes.
Okay. And do you think that these two normals are actually precise?
Yes. We think it's precise because we have let these two omega by omega 2 into our general solution, and we find a pretty fit.
So it fits with your experiment.
Yes.
Do you think if you added more data points and put it into the fast Fourier transform, would the spike become more discrete?
Discrete?
Yes.
You mean
like maybe the amplitude would be larger, and you could see the two normals.
So you can see in this data, when the time increase, they're actually not fitting very well, and the initial is fitting well. So when the time becomes larger, it means the theory and the experiment becomes very large because every system will influence.
I think this might be caused probably because of the error distance and also the exponential.
Yes.
Okay. Yes. Okay. And next, the other thing I want to ask you is, so you considered the error resistance in your theory and also in the experiment. So what about the friction on the connection points when they're connecting?
The pendulum and the spring.
Yeah, and also the spring and the fan. Will there be?
I agree with the spring and the fan because actually the spring and the fan have a friction, but we didn't consider. So it might be a little cause of the exponential decay. But however, I think every system plays the greatest role.
Okay, thank you.
Okay.
Okay, opponent, please summarize the discussion.
Okay, so in our discussion, I talked with the reporter, and we also compared our thoughts on the theory and also how it affected the experiment, the theory fitting line, and also some assumptions he made on theory. And I think that in his theory, he did a pretty good calculation, so he got a pretty good fitting curve to his experimental data. And I also think it was a really good idea to consider the error resistance, and so he could further explain the exponential decay as we see here. And another thing that was really important was how the energy transfers between these two modes. And so I think that it is because of the helical spring structure that causes the energy transfer between the longitudinal and rotational. And the opponent, the reporter thinks that it is also, it may also be caused by the spring structure and then also the coupling constant.
Okay. So the reviewer, you ask question to the reporter and opponent.
Okay,
3
thank
minutes.
you.
Okay, please.
Thank you for reporter and opponent. And can you turn to page 5?
Right.
Yes. Can you explain what this is 1/2?
So this because this found from our references. Because reference told us that the coupling term is actually a potential and a kind of a potential energy. So we added in the Lagrange. You mean why it write like this?
Yeah, no. In my opinion, I think this might be like 1/3 or. It's a relation between Z and theta, right?
Yeah, the relation between Z and theta. But this term is actually just a term. It's like why we write the kinetic energy as this? It's the same meaning. Yes.
Do you think if you change the constant of the spring will influence the conclusion that you mentioned, the vertical frequency and theta?
Oh, yes. So when we change the constant of spring, it will affect the frequencies of a normal mode. So it will affect the result as well.
Okay, I think if they change the spring, it will directly affect the natural frequencies and also affect the normal frequencies.
Okay, and how about if you change the mass of the paper?
Oh, as well, the mass have been concluded in our general motion. So when the mass change, means the moment of inertia will also change. So it will affect the results.
The mass will also change the natural frequency and moment of inertia. So I think it's the same as changing the spring.
Okay, and can you show the figure that the CTAS figures?
You like
CTAS.
theta figures?
Yes.
Oh, for example, this one.
So the line is in decrease. So
Yeah, decrease.
why? It's a damping effect.
Because I have mentioned why it decreased is because of the air resistance, and I have the discussion with the opponent that maybe the friction force between the spring and the point we fix it, and have also a small friction force we also need to be considered. So it's about the resistance and mainly the air resistance.
And why at the end of the data the frequency is not very fit to the theoretical result?
So I think this a little bit of our experimental mistake, because in our condition on the top of the spring, the spring at the fixed point is actually will have a little spin. So I think this maybe we can improve our experiment and fix this mistake.
And that's why.
Okay. We only have 2 minutes for preparation. Please take the floor.
Other judges and every competitor. I'm from Teaching Academy and my name is Josh Lee. Today I'm going to review the problem 2 of Wilberforce pendulum. Problem statement: a Wilberforce pendulum consists of a mass standing from a vertically oriented helical spring. The mass can both move up and down on the spring and rotate about its vertical axis. So what we are going to do is to investigate the behavior of such a pendulum and how it depends on the relevant parameters. And this is our reporter's portion count. So we see he is good at the explanation and analysis of the theory, and using the program as the ideal state. And we'll comparing the theory line and the experimental data. And the counts is until experience setup and the lack of the photograph record, and not enough variables, and can spend more time on the experiment instead of the theory. And opponent give out the clean opinion of the questions and getting the reporter's agreement. And the cons is the lack of a discussion on experimental setup and result. And second is give too much discussion on the calculation.
And discussion, the opponent as the constant data, and the reverse applied by the theory. And a reverse opinion is display of the theory result in experimental proof. And the second question, opponent asks the energy transfer, spring affect the transport and spring constant. And the reporters say rotating didn't affect the much of it. And the reverse opinions agree with opponent and rotate cause energy loss. And the third question, opponent asks the experimental result compared to the theory line. The reporter's answer is effect over height because of the air resist and resistance. So, and first, the question is constant of the spring mass of the pendulum, and the opponent affect the force, and reporter affect the frequency and normal frequency, and reverse is affect the kinetic energy. A question that asks the experimental result compared to the theory law, and opponent say mistake. So we think this is that they can improve. And a conclusion, we think that the reporter can think more about the sum of that 1/2, because I think that situation need to be like the hook spring, and that will be 1/2. And this is my review. Thank you.
Okay. So, reporter, please take the floor.
Okay, so for the concluding part, first we have well discussion with the opponents, and air resistance was the main reason of the exponential decay. Also, friction force that we discussed between spring and the physics we need to be also maybe need to be considered. And second, the main reason energy transfer is caused by helical spring and a coupling term, which the opponents and we agree. And normal modes will be affected under different conditions. For example, when we change the different spring, it will be affected. And we can improve our experimental setup and try to minimize the error, because there are actually some error caused by our unclear experimental setup. And number 5, when turning the pendulum of positive 90 degrees or negative 90 degrees, well, we find only one normal mode, which is different from our assumption. So maybe in our future theory, we can find what conditions will it cause only one normal frequencies. Maybe there's other condition that we didn't find. So just like opponent said, maybe we can change the lead direction and the theta direction at the same time and find whether it will have one normal frequencies in our future work. And that's the general motion in our theory is mostly applicable, but however, it will still be affected by some unclear experimental setup, and also the air resistance, also some friction we ignored. So I think in this competition we have well discussed and have a better understanding of the theory, and also find some mistakes of our experiments and well discussed for the reviewer and the opponents. And thank you.
Okay. So it's time for the question for the jury. Any question for the jury? Professor John, please.
Yes, I have a small question for you. Can you go to the page 28? I found some missing points there. Maybe some errors. Can you explain page 28? Yeah, this one. Around the 25 seconds. Do you see the bright spot? The magnet, yeah, this one.
This because our experimental, because we because we have many data points, so maybe we have a wrong. I get a wrong data point from here. Our data mistake. Yeah.
Okay. So the second question is about do you also consider the limit of the spring, like the electrical limit of the spring?
The limitation of the spring.
Yeah.
It's like the structure of it.
Yeah, the torsion of the spring.
Oh, okay. So I believe when the structure different and the torsion constant will be different, and the spring constant will also be different. So I didn't consider it because I only use the same spring. So yes, it will be affected.
Okay. I mean, in my opinions, I think because we do the experiment, right?
Yes.
So I also want to consider the spring constant, the limit of spring constant probably put a lot of mass of the this material, and then you will damage your springs. You want me to go out the spring limits? I think maybe not. I don't know. I just want to make sure. Do you also consider this one when you pick out the different mass for this product?
I only use the same mass.
Yeah, so I just want to know the limits. It's a mass, but this mass is already arrived to the mass.
Maybe we can test it in our future work.
Yeah.
Okay, thank you.
Okay, any question from jury? No further question? Then it's time for the story. Okay. So let's show the score of the reporter. Eight, 7, 7, and 8. Can we show score for the opponent? 7, 8, 7, 7, 6, and 8. Can we show score for the review? 6, 7, 7, 6, and 6, and 7. So, any comment from the jury? No comment. Then we close the file this morning. Let's give everyone a big hand. Thank you, everyone.